Hi folks, welcome to New Electromagnetism video number 2, where we're going to discuss how inductors really work with a little caveat to electroinertia. Okay, so we're going to talk about what inductors are, what they do. I'm going to show how they work. I'm going to try to explain them using classical theory, and you're going to see the nonsense that goes on trying to explain inductors in classical theory. And then we'll explain them using new electromagnetism using the inertial force. And then at the end, we're going to begin the discussion how to properly measure inductance. So what's an inductor? An inductor is essentially a loop of wire. Now, you'll notice these are all shorted together because the purpose of this is so I could change what contacts I use for which circle using an X-Acto blade. So don't mind that they're all shorted here on this, but essentially a loop of wire. And then a coil of wire is another kind of inductor where by having multiple loops ganged together in a coil, you can increase the inductance dramatically. You can also increase the inductance again by putting not an air core, which this is, but a ferrite core in the loop, the coil of wire. The symbol for an inductor looks like this. It looks like a stretched out coil. And the symbol we use is L. Why they use L instead of like I for inductor? Well, I is already taken to represent current, so I think L was the next logical choice for a letter to represent inductors. And this is consistent. There's a lot of letters that don't represent things in electrical engineering, like Q is a transistor, U is an integrated circuit, yada, yada, yada. That's common convention that everybody has adopted. So what does an inductor do? An inductor opposes the change in current through it. And the analogy is a flywheel, where the velocity of the flywheel is analogous to the current in an inductor. Okay, so here is a flywheel with a little handle. Okay, if you were to try to apply a force to this handle to try to rotate the wheel, the inertia of the wheel, or moment of inertia, depending on how you want to parameterize it, is going to oppose you and make it difficult for you to get this wheel going. This heaviness is what inductance is in electrical circuits. So if you were to take this flywheel and you were to apply a force, well, because of the mass, they say, right? We say inertia in the Ethereal Mechanics. Because of the inertia of the wheel, it's going to oppose you. And, okay, usually when we talk about spinning systems, we talk about moment of inertia and torque. But for the sake of simplicity, you could also parameterize it as effective mass and force opposing the applied force. So the force you're going to feel on your hand is going to be the effective mass of the wheel based on moment of inertia times the rate of acceleration. Okay, this is the inertial force because this sign is negative. It opposes the applied force. This is the inertial force that's going to oppose your ability to try to accelerate the wheel. But what will happen, though, is this isn't perfectly equal and opposite, which will allow the wheel to start spinning. And over time, eventually the wheel's going to accelerate, and then you're going to come to a time where the velocity of the wheel, the speed of the wheel, is going to saturate. And the reason why this saturates is because you can only turn your hand so fast. In other words, if you've ever done this before, like if you ever tried to spin your bicycle by spinning the pedals by hand, there's only so fast you can move your hand around in a circle to get that bicycle wheel going. And you are limited by the limited ability of your hand to apply more force to it. And so you get to the point where you cannot move fast enough to apply more force, and you get this saturation or this top speed. Okay, and so the same thing with an inductor. Here's the inductor, and you apply a voltage source to the inductor. The minute the current in the inductor starts moving, starts accelerating, that's what this is, the change in current. Okay, you get an opposing voltage that opposes the applied voltage, and it reduces or retards the ability to get the current moving through the inductor. Okay, but again, over time, that's going to break down, and eventually the current is going to start increasing to the point where it's going to saturate. And the reason why it saturates here is because no voltage source is perfect, and they have a built-in source resistance, and that's going to limit how much current you can actually push through the inductor. So in this case, the current through the inductor and the speed of the wheel are analogous to each other. But as we found out in the electrogravity series, the inertia of matter is in fact due to electromagnetic induction. That's why this is called electroinertia. But if you want to see that, go back to the electrogravity series where we actually derive the mass from the inertial force model. This isn't that. This is just to explain inductors for circuit analysis, for circuit theory. Next, once you get the wheel up to speed and then you stop, you remove your hand from the crank, okay, excuse me, the wheel, energy in the wheel is going to bleed off slowly because of the friction in the hub and because of air friction. Same with the inductor. If you remove the voltage source and replace it with a short circuit, the inductor will keep pumping the current around like the inertia of the wheel until the resistance finally drains the energy out of the inductor, and both systems will slow down at a decay curve like this. I have not updated these models up here to show this. Okay, and the third case is once you get this wheel up to speed and you get the current through the inductor, if you try to stop this instantly using your arm, you could possibly break your arm. That's how much inertial force is there, or inertial energy. Same with the inductor. If you just, instead of shorting the loop, if you open the loop, not allowing the current to go anywhere, the voltage across this inductor could be hundreds or thousands of volts, because that inductor is going to try to keep that current going. This is what they call inductive kick. This is used to make cattle prods and zappers and all kinds of high voltage sparking, arcing devices. Again, I didn't update these models for this case here. Okay, so that is how the inertia in a wheel and the inductance of an inductor are analogous to each other. How they work the same, where you can treat the current in an inductor the same as the speed of a flywheel. Now, for your information, typically whenever inductors are used, this can include motor windings, any kind of coil of wire like motor windings or such, they typically put protection diodes in there such that if you turn off the voltage source, instead of that energy and that inductive kick trying to trash through your voltage source, it'll just short through the diode, and that'll protect your transistor circuit or whatever you have over here. Now, this is only one methodology. There's lots of other different diode protection schemes out there. I'm only showing you one here just as an example that diode protection schemes are probably the most popular. And sometimes even they'll even have back-to-back Zener diodes here. There's lots of other variations on the protection schemes to protect your active circuits against inductive kick. So next, we're going to explain how inductors work. First, we're going to show you using classical theory, and then we're going to show you how ridiculous classical theory is. In fact, we're going to show you really can't even get an answer with classical theory. And for those people that are going to start grumbling about vector magnetic potentials, we'll discuss that. Then we're going to explain how inductors work using new electromagnetism. I'll show you it's very, very easy. It's very simple. It fits in your brain a lot easier than this stuff up here. What I tried to do is go out and see if somebody had a video that explained how inductors work using classical theory. Instead of explaining how inductors work, I showed there's a lot of videos out there and animations that are nice that show what inductors do. So if you want to go look at those, they'll show you what inductors do using like a water analogy here, which is very good. But it doesn't explain how inductors work. It explains what they do. So I couldn't go and use somebody else's graphics or imagery because there isn't any for that. So the first part of explaining how inductors work, you need to understand basic magnetic field. If you have a current in a wire, a current moving through a wire generates rings of a magnetic field. Now, this model is just to model. These magnetic field rings, whether they exist or not, is irrelevant. The model is pretty decent. But one of the problems I have with this model is when you have a current moving through wire, how does this ring get out here? So somewhere out at a distance from this ring, there is a circulating disturbance, but there's no explanation of how the current in the wire gets to this point out here. That is a violation of locality. Okay, which showed, now that doesn't mean the model is wrong, it just means there's a lot of missing details in the model. Okay, and we're not going to come back to that because Ethereal Mechanics explains this a lot better, and we don't use the B field analogy anymore. But going back, because we are trying to explain it using classical theory, so you can imagine we have a loop of wire, and we have a current flowing in the loop of wire. And because of using the right-hand rule, this is going to create flux lines that are going down into the page on the interior of the loop and coming up out of the page on outside of the loop. And what we do is we show flux lines going into the page using crosses. It's like you're looking at the back of an arrow, the fins on the back of an arrow. And that's how, and this is a common standard usage throughout the industry. So this is a normal, everybody uses this same diagrammatic representation. I'm not inventing anything new here. Okay, and so these X's represent flux lines going down into the page. Over here, these dots represent the tips of the arrow, and so these represent the arrows coming up out of the page, or the flux lines coming up out of the page. Okay, so now what I want to do in order to show inductance is I want to increase this current. Now, according to Faraday's law, trying to increase this current is going to create an EMF that's proportional to the number of loops, the number of turns, and this is only a single turn inductor, so N is 1, times d phi dt. What d phi dt means, really it means, we should use dx dt here in this case, but d phi dt means the number of these lines, which are represented by x's, the change in the number of lines. So by trying to increase the current, if that causes 10 more lines to increase here, then that d phi dt is 10, and that's going to create an EMF. Now you need to use Lenz's law to understand which direction the induced current is going to be. So if I'm increasing the current here, that's going to increase the number of x's here. Then according to Lenz's law, the current in the wire is going to induce a current in the opposite direction to oppose the change. See how confusing that is? So here we have another problem here. So in other words, if another X pops up over here, according to this, it's going to cause an EMF in the wire. So how does something appearing here affect the wire? There's no explanation of that. So this is a violation of locality. Now, in the rules of acquisition, which we handle locality a little bit different than classical physics. Locality, a violation of locality, is a violation of ambiguity. And ambiguity doesn't mean your model is wrong. It means you do not have the most fundamental. It could mean your model is wrong, but it could also mean you don't have the most fundamental expression of your model. Okay, so violations of locality are handled in accordance with the ambiguity tell, which is rule of acquisition number 17. And that means that either your model is wrong or you don't have the most fundamental expression of your model. Those are the two things that come about when you don't, that cause ambiguity. Because another ambiguity that drives me up the wall with Faraday's law is, well, okay, how does a flux line here affect the loop but not any change in flux out here? How does that work? How does the wire know that these flux lines are on the inside and these are on the outside? It will cause the wire to be smart, and that violates the sentiency rule. Okay, you cannot have anything in basic physics to be sentient. And so you have all this stuff that doesn't make any sense. This is also the bigger problem with this. When using Faraday law, the biggest problem, even worse than the ambiguity tell and the locality tell, is the fact that Faraday's law does not give you an answer for self-inductance. Okay, I tried. When I first started saying I need to understand how inductors work, and I went through a lot of numerical methods, a lot of mathematics even, trying to come up and get a valid answer for an inductor using field theory, I could not do it. Okay, and the reason why is because you have to integrate your magnetic field as your distance goes to 0 to this loop of wire. And as that distance goes to 0, your answer for inductance goes to infinity. This is what we call a singularity. So there's the irony is that Faraday's law cannot give you an answer for self-inductance. It works fine for mutual inductance, but you cannot get an answer for self-inductance. You get a singularity. That is a fundamental flaw, and that is the biggest reason why Faraday's law is garbage when it comes to self-inductance. Now, there is a thing called vector magnetic potentials. Oh, wait, is that next? No, before I talk about that, the measured value for a loop of wire, and this is measured and confirmed, is if you take mu naught times the radius of a loop of wire times 8 times the radius, it's a natural log of 8 times the radius divided by the W, which would be the radius of the wire. So you get the radius of the loop, which is measured from the center out, and the radius of the wire is basically the radius basically the thickness of the wire. This gives you dead-on, balls accurate for the inductance of a loop of wire using round wire. Now, there is a solution using vector magnetic potentials. And if you go into the book, problem 5.32 of Classical Electrodynamics, 3rd edition by John David Jackson, he says that the inductance of this loop is this, and this does not match the measured value. Okay, now, to be fair, if you go to my graduate thesis or even go to the foundation series, I show you that Jackson has an error in his derivation and that you can correct his derivation to get this answer up here. The problem I have, the bigger problem is then this is derived using vector magnetic potentials. How does vector magnetic potentials give us an answer if it is derived from legacy theory? If it's derived from legacy theory, it shouldn't give any answers more or less than what classical theory could give. Okay, so I think there's funny business going on here with this derivation. Now, I haven't gone back to check on it. I want to one day when I got time. But the important thing is that new electromagnetism, new induction, okay, has no problem getting the right answer, and the derivation is a hell of a lot simpler, and the derivation, it makes a lot more sense than the vector magnetic potential derivation. So I'm not even going to bother going back to this, even if I could verify that they weren't doing funny business, which makes no sense. Because if the classical models say can't be an answer, there's a singularity, there has to be a singularity in anything derived therefrom. So again, in the foundation series, I do correct Jackson's derivation so it does match. But again, if the basic models cannot give an answer, how does a vector magnetic potentials give an answer? And I'm going to leave this to others to figure out. Okay, but one of the problems from both vector magnetic potentials and Faraday's law is that you can't explain the inductance of a dipole antenna. Because in Faraday's law, you need your loop of wire to close a set of flux lines. Well, in a dipole antenna, no flux lines are enclosed. And when you're using vector magnetic potentials, if you look at Hayt, H-A-Y-T, that's the last name of the book, a famous author of magnetic books, there's a stipulation that when you use vector magnetic potentials, it has to be applied to closed loops. Otherwise, any derivation from vector magnetic potentials is bogus. Okay, this is not a problem for new induction. New induction does not talk about the flux lines enclosed. New induction talks about everything pretty much occurring where the wire is. And because of that, we don't violate locality. So let's talk about how we use new induction to explain how inductors work using the inertial force model. So the inertial force model says if you have a source charge that's accelerating, it's going to create a disturbance in space that's going to travel at the speed of light, and it's going to travel in all directions. It travels spherically from the point of disturbance. And the other charges it affects, it's going to apply a force to them that's in the opposite direction to the acceleration of the source. And this is the simple equation that defines that effect. And this effect minimizes, or it diminishes by distance. So the farther away this is from this, the smaller the effect will be felt. This is a simple point charge model. It has nothing to do with flux lines. It has nothing to do with vector magnetic potential. It's just a simple point charge force model. It's so simple, even a physicist can do it. And look, if you look closely, this is F equals ma. We'll cover this in more detail toward the end. Okay, but now, suppose that you had a whole mess of charges here, and you tried to accelerate them using an electric field. So we have a positively charged plate here and a negatively charged plate. So we're trying to accelerate these guys all uniformly. Well, the reactive force or the inertial force felt by this guy is some contribution from the effects of this guy, and this guy, and all the charges that are in the area. I'm just showing 4. So the more charges that are here, the more inertial force this guy is going to feel from his companion charges. Okay, so now if we go and look at a loop of wire and we try to apply a voltage to increase the current in this direction, well, now because all of these charges are trying to be accelerated by the applied electric field, them all reacting to each other is going to cause an intense reactive inertial force that's going to oppose that attempt to accelerate them. Now, this effect also travels through space to the other side of the loop. And the effect over the is going to be very, very small when it finally gets there. But this effect will also be upward over here, which minimizes a little bit the force here. And that happens all the way around the loop. Okay, so you have to couple all the charges to each other all the way across the loop to properly compute the inductance of a loop. And I've done that with the software for my graduate thesis. We'll be releasing a new version of that. And we get dead-on balls, accurate answers. And with this technique, we can also get the inductance of inductor sandwich between ground planes and dual ground planes, which you cannot do with classical theory, or more appropriately, I have not seen anybody do it with classical theory. This is so simple, a physicist can do it. Now, let's crunch that loop down to decrease the distance from one side of the loop to the other. So as we apply our force, our electric field, or electric voltage here, trying to accelerate all the charges in the loop, we're only going to look at a small section. These charges here are now under the electric field to start accelerating. And because they're starting to accelerate, they're going to create an inertial force which is going to oppose the applied force which is trying to accelerate them. They're electroinertia. But these guys on this side are also accelerating, but they're accelerating in the opposite direction. And because they're also going to emit a field, and their force is going to, and their inertial force is going to be in the opposite direction because they're accelerating up. Now, this field that they're generating is going to travel across and apply to these guys too. So the net effect of these guys is their inertia field subtracted by their field. So by closing the loop, their field is going to be mitigated by the field that has to travel across the loop, so it's going to be mitigated a bit. And so their total inertia is reduced drastically. And so that's why when you take the area out of a loop, its inductance goes way down, is because the opposing side of the loops cancel their inertial fields. I hope that explanation was clear. Now, let's take this one step further. Let's make this loop 1,000 miles long. And what we're going to do, we're going to focus on this little area over here. Okay, now I'm still using engineering terminology where we engineers use positive charges as the mobile charges. Okay, but I'm also going to be discussing, we need to look at the non-mobile charges, the negative charges in this case. I know it's backwards. I know in reality, physicists in 1922 determined that electrons were the mobile carriers and the positive charges make up the nucleus and they don't move. But we electrical engineers have been using this positive current model since like the days of Benjamin Franklin, for at least 100 years before physicists came up. And that's just an example to show you how humans usually get stuff backwards before they get it right. But in this case, modeling things backwards, as long as you do it consistently, this doesn't really affect our answer. So just as a caveat, yes, I'm still using electrical engineering notation where it's a positive current that flows, but we know in reality it's really the negative charges. Okay, so just, I forgot to mention that before. Okay, so now what if we now apply a voltage source to the right? Well, what's going to happen is that voltage source is going to pump mobile carriers out of one side and shove them into the other side. So that's where you have this concentration of positive mobile carriers and a depletion of mobile carriers here. Okay, and we can do that because this sets up like a little local capacitance between this side, which allows us to do that. Okay, and because we've done that, we've now have a current change in this direction, which causes an inertial force in the opposite direction. But interestingly enough, just like we showed you in the previous example, even though the force is bigger on this side, the force is felt on the other side as well. Because remember, that force travels spherically in all directions. So the effect of this current change in the leads of the wire is going to affect the opposite side of the loop and cause current to travel in the opposite direction. Such that if you put a light bulb here, you will notice an effect. A light bulb or LED will in fact glow. And this will occur long before the current sets up in the rest of the thousands of miles of the loop. Okay, such that you don't really need the rest of the loop. Okay, you can have this effect. You can actually put an AC circuit, an AC frequency source as your voltage source, and this effect will transmit across the gap from left to right, and it'll have nothing to do with the rest of the loop because AC will be so much higher frequency than the loop is that you can actually power this light from a voltage source on this side of the loop. And then such in fact that if you cut the wires at the lambda over 2 based on the frequency of this AC source, okay, then you basically have reinvented radio. That's how a dipole works. Remember I told you in the beginning, Faraday's law does not work for a dipole antenna. It most certainly does for new electromagnetism, and this explains how radio works. A radio wave is an inertial wave. It's one of its primary. There's another component in there, the magnetic component, but the inertial component is the primary component of electromagnetic radiation. Okay, that I've already proven. If you look at new induction applications, version 1, we have dipole modeling there in that application paper. And this is funny because this whole thing is produced by Derek of Veritasium of the thing how electricity acts. He goes, electricity does not flow in wires is the argument. And what he has is a very long experiment with a switch and a battery source on one side and then a detector on the other side, and it works. And it's basically saying, whoa, and then he's got everybody all in an uproar. He's got all these other copycat science sites all regurgitating his work. Some people are saying, oh, he's full of crap. It doesn't work. When it does work, because it's basically radio. And then you have people out there, his detractors, trying to apply lumped circuit analysis to disprove that, because he's trying to make the argument that somehow it's faster than the speed of light. It's like, no, it's just traveling across the gap. There's no problem here. It's just radio. All he's done is reinvent radio. We're going to call him Derek Marconi to be funny. Okay, and the detractors, and I've just watched the videos, and I want to howl at the moon for the very poor theoretical applications trying to explain this. It's just frickin' radio. It's been around for 100 years, and you get and this just shows how poor training is in electromagnetic theory, and not as only poor training, but if you just look at the electromagnetic models and show you how bad it is trying to explain inductors, you can't explain inductors with it. And, and it's just the models themselves are so bad that they leave people in all kinds of bad directions. And I see all of that going on with Derek's followers, the sites that are verifying Derek's work, and the other sites that are just trying to discredit Derek's work here. So, Derek, thank you very much. You've made my job harder. It's about time we shit can classical electromagnetic theory. It is horrible. You can see by the example that it doesn't explain inductance is the main reason why it's horrible. Okay, and this is going to illustrate. A lie can travel completely around the world 3 times before the truth even gets out of bed. But Good thing is, slow and steady wins the race, and the truth always prevails in the end. Okay, and one of the funny claims from Derek and some of his people out there is that power or electricity, some say one says one says the other, does not flow in wires. Then my question for them is, well, try to do your experiment without wires then. Okay, this is where I have to look at something beautiful and peaceful to let my blood pressure come down. Okay, this is a scene out on my back deck of the valleys on a beautiful autumn morning. Peace and quiet. Now, let's go on with the rest of the video. Now that I've got my blood pressure back down from having to deal with this classical theory nonsense. So, one of the beautiful things of new induction is that the reason why I call it the inertial force is because, remember, the inertial force of the flywheel, I mean, granted, we're using it not quite right. We should be using moment of inertia, but it's all basically the same physics. F equals minus ma. This is the inertial force. This is the force that reacts to an applied force. That's why the minus sign. The inertial force of new induction, same thing. It's an applied voltage. This is the force that reacts to trying to accelerate charge. This is a force reacting to trying to accelerate charge. Okay, and then if you set these equal, then you find out that mass, what they call mass, I call it inertia, is km times q squared, coulomb squared over distance. And if you work out the units, that works out to kilograms. That's what they call mass. I call it inertia. Okay, now the natural units of inertia are just square coulombs per meter, and that's what we call the Burl. The reason why we're using legacy units here for new electromagnetism is because all the instrumentation that we're going to use to make measurements still make measurements using legacy units. So that's why we have the blue. Because you get rid of the blue, that's all natural units. And again, it's the same thing. You try to accelerate the wheel, and you get an inertial force that opposes you. You try to accelerate charge in a loop, you get an inertial force which opposes you. And this, if you look at the electrogravity series, we basically show that matter is derived from pretonic charge, which has no intrinsic mass or no intrinsic inertia. All inertia is electromagnetic in origin. This is the first theory that has ever said that. There have been theories in the past that tried to do it, but they tried to do it using Maxwell's equations, and they failed miserably. Because everybody wants to believe Maxwell's equation. I don't know why. They're horrible. They got two definitions for magnetic fields, which is completely useless. They got two definitions for an electric field. Completely useless. Oh, better stop getting my blood pressure up again. Peace. Okay. So what we're going to talk about now is the next upcoming videos where we're going to remeasure the experiments I did on my thesis using a better method of measuring inductance rather than the Agilent LCR meter. Okay, and what we're going to do is the problem of using the Agilent LCR meter is the Agilent LCR meter measures inductance using an AC signal. And the problem with a AC voltage varying signal is that you get voltage coupling between the loops of the wire, capacitive coupling. And that capacitive coupling creates capacitive reactance, which dilutes the inductive reactance we're trying to measure. And the Agilent ACR meter only gives you the net reactance. Okay, so if you have capacitive reactance in there, you are interfering with your ability to measure the inductive reactance. Okay, that is the fundamental problem. So what we need to do is measure the inductance by keeping the voltage across the inductor constant. If we keep the voltage across the inductor constant, there'll be no capacitive coupling from the loops of the inductor. And we can see that, we can do that from the model. By keeping the voltage constant, all we have to do here is have a constant current change. So if we can keep supplying current, increasing the current at a constant rate, at a ramp, like a ramp of current, that will keep the voltage constant. And then we can, the slope of the ramp will be proportional to the inductance. And this is what I call the current ramp inductance measuring circuit, where we use a field effect transistor and we have a control circuit that'll keep the voltage at this point constant by changing however it needs to change the voltage at the control input of a FET. And then what we do is we measure the current draw across a low inductance resistor, and that will allow us then to determine, based on the voltage step and the current draw through the resistor, we can divide those out to find out what the inductance is. Now, the caveat here is that the inductor isn't a pure inductance. It also has resistance. And this resistance does affect our measurement, so we have to account for it. And this is the equation we use here. Now, the rest of the videos going forward are going to be for Patreon members only. We're going to show the detailed design of this system. And there, again, to people that aren't going to become Patreon members, there's other things you need here. You need a protection diode here, like we described before. You're going to need protection on here to prevent electrostatic damage of this. You're also going to need termination resistors. And you probably need a lot of capacitance up here because you want to keep this voltage constant as the current ramps. So you need a whole crap load of capacitance. There's probably some other things I forgot, but normal engineering stuff, engineering techniques are for those things there. Okay, so in the next couple of videos, we're going to show the design, the more detailed design, component selection, and construction and initial testing. And the software will be only for Patreon members only. If this is sometime in the future and you want to go back now, you're watching this and go to the Patreon and find them, the tags will be CRIM, New Electromagnetism version 5, or NEV5. The final video of the new induction series, we're going to show the measurement results to everybody. We're not going to keep them secret. And we're going to compare the values obtained, compare them to the values obtained using the Agilent LCR meter. Now, to be fair, the Agilent LCR meter is probably the better type of measurement if you're going to actually put the inductors into use, to put them into real circuits. Okay, the CRIM is there to verify theory. Okay, that's to verify theory because we need to minimize the capacitive reactance so that we can validate the theory. But it's not the means of measuring for actual use in a circuit. In that case, you're going to want to measure it closer to how your circuit's going to use it, and that's probably going to be your Agilent LCR meter is going to be the better way because you are going to have capacitive reactance between the loops of your inductor, and that is going to be important to you in a real circuit application. Okay, let me just be clear. The CRIM is only for validating the induction theory. Okay, I'm not begging anymore. I realize new electromagnetism is niche. I respect my Patreon members. I have a lot of Patreon members that are engineers, and they've been very helpful, and I appreciate them tremendously. So if you want to become part of the people that are going to be riding the wave of the future through all the bilge and nonsense that's out there, please, $5 a month will get you passenger, and you get to see all of the videos going on of how all the stuff gets built and designed. And you're going to see a lot of other stuff before the regular people see it. A lot of the stuff that's eventually made public is shown to Patreon members first. So thank you very much. No more voodoo physics.